If you get asked to write about the water cycle on an FRQ, make sure you include what drives the cycle, what pushes it, and that would be the sun. Don't ever leave the sun out. It's very important. That's the energy that causes this whole side of the cycle to work. So the process of evaporation is caused by the energy of the sun heating up the water. The cycle itself is really just two things. You've got water moving to the atmosphere, and you've got water moving back to the hydrosphere. Another word that some people don't really know is transpiration. Transpiration is just evaporation through a plant. The water can go along the surface. That's called runoff. The water can go into the ground. That's called infiltration. Percolation is when water goes through the pore spaces in the soil. Remember, that's also a form of natural filtration. But eventually all that water tries to make its way back to the ocean, either through the surface as a river or through the ground. It makes its way back to sea level because of gravity. 97% of the water on Earth is in the ocean, which means that it's salty, and therefore we can't use it for drinking water. There are ways to take the salt out, but it's not very efficient or economic, also not very environmentally sound. We'll get to all that next semester, actually. So that leaves 3%, okay? 3% of the Earth's water is what we call fresh water. So if we look at that tiny little 3% that's left, that doesn't mean that we have 3% of the world's water that's usable to us, because two-thirds of that water is frozen. It's in the ice caps, and it's on mountaintops as glaciers. So for you math majors out there, that means that we have about 1% of the Earth's water that is usable fresh water. Out of that 1%, most of it, almost 99%, is in the ground. It's in a place that we call aquifers. We'll learn about those. And that's where we get most of our drinking water, most of the water that we use for showers and dishes and laundry and watering the grass. All that comes from the ground. So the first one I chose was salinity, which is how much salt is in the water. Obviously, some organisms can live in salt water and some need fresh water. I've actually previewed 3 of the biomes here when I say we've got fresh water, like a river, which eventually becomes an estuary. That's where a river empties into an ocean, that transition zone. And then the ocean, of course, would be salty and its own biome. The ocean is also able to uptake by itself. It's able to absorb carbon dioxide. And so when we burn fossil fuels, that puts more carbon dioxide into the ocean. And that's the same stuff that's in your soda, right? Your pop. Turning the ocean more acidic and killing off reefs. Okay, next up we've got depth. And depth primarily affects photosynthesis, right? So if you have organisms that can grow, they need sunlight. But the light can only penetrate so far down into the water. So the deeper you go, the less chance there is of something growing and producing oxygen. The diagram I have on the right talks about the photic zone. And photo means light. And pretty much all wavelengths get down into there at least a little bit. And then once you get below that, we've got kind of they call it the twilight, the dysphotic zone. But eventually you get to aphotic, right? Just like biotic and abiotic. Aphotic means without light. And there are things that live there, right? There's organisms that have adapted and can still be primary producers. They make their own energy from what's around them. They can use the heat from thermal vents on the bottom of the ocean. Turbidity might be a new word for some of you. It means how cloudy the water is, how cloudy it is. So we talk about the muddy Mississippi, right? All kinds of sediment gets washed through the watersheds and ends up in the Mississippi River. And it's just brown and gross. Some streams and rivers flow faster than others. that is going to affect how much oxygen is in the water. And yes, animals that live in the water still need oxygen. Also, if it's a plant that's trying to sustain roots into the riverbed, well, if the river is moving too fast, they're not gonna be able to anchor. Or if it's an organism that clings to rocks, if there's a flood, that can sweep them away because it's flowing too fast. And also, some animals or plants sit there and wait for food to come past them. I'm thinking of there's a coral that the water comes into it and it eats that way. So it doesn't hunt or chase or anything. It just waits for the food to come by. And if the water stops flowing, then it gets less food. Nutrients. So sometimes nutrients in the water are good and the organisms need them. And sometimes the nutrients can be bad. So when we have fertilizer that runs off, that's called eutrophication. We're going to do more with this word too, because it's a big, important concept. Eutrophication means an excess of a nutrient, where you actually can have too much of something. In the case of fertilizer, it's usually nitrogen. So nitrogen washes out and ends up in our water. And guess who loves nitrogen? Algae loves it. So we'll get algal blooms. It kills everything underneath it because it blocks out the sun. It hogs all the nutrients itself. So eutrophication is considered bad, and it's also a human impact when it's a result of fertilizer. We have studied and found out that light can also affect dissolved oxygen. So rivers that are more shaded and have woods around them, they're going to have more dissolved oxygen in them. And ones that are out in the sunlight that are warmer, they don't hold as much dissolved oxygen. So sunlight can actually heat up the water and remove oxygen from the system. All right, that was all pretty technical stuff, not very fun. So I thank you for your attention today, and we'll get you out of here and we'll do a little more tomorrow. See ya.